Okay, good morning, guys. I guess we're going to continue on through the material. So right now we're going to be jumping chapters. So we're going to move from chapter 16 to 17. And today's material is the Fourier transform. Okay, and I want to cover 17.1 through 17.4 if you want to follow along in the book. Yeah. Okay, so last time we talked a lot about the Fourier series. Okay, now if you remember the Fourier series, we can set it up in an alternative form where it's f of t is equal to this, and this is the complex exponential form. Okay, and then to find the CNs, those coefficients, we just do an integral. Okay. Cool. Okay, now obviously you see how I set the limit to the integration. This assumes we want to start at negative t halves to positive t halves. Okay. Now we can sort of manipulate this a bit. So what we're going to do is we're going to let the period go to infinity. Okay. So when we did Fourier series, we always assumed that the function was periodic, right? So what we're doing now is we're going to say, okay, that's cool, but what we're going to do is we're going to push out the period all the way to infinity, okay? And the result of this, we can see the harmonics get closer, okay? And that would make sense, because if omega naught is equal to 2 pi over big T, okay, we can say that the adjacent harmonic, say we have like n plus 1 times omega naught minus n omega naught, that's still omega equal to omega naught. But this difference between these two, n plus 1 omega naught and n omega naught, that's going to get smaller as big T gets bigger. Okay? So that is all to say that delta omega gets smaller as big T gets gets bigger. Okay? Similarly, if big T goes all the way to infinity, then delta omega, then we can say it's just d omega at that point, okay? Cool. So we can say that if we have 1 over big T, then that'll turn into d omega over 2 pi. Because remember, we need to include this 2 pi factor right here. Since we have 1 over big T, we just need to divide both sides by 2 pi to get that. Okay, cool. Now, interestingly, if we go back to this equation right here, we can multiply both sides by big T, okay? So we can say that Cn times big T is equal to, now, since big T's gone to 0, the limited integration have gone to negative infinity to positive infinity. Okay, ft, that hasn't changed. Now, n omega naught, we're just going to let that be just omega now. Dt, okay? Again, this is as big T goes to infinity. Okay, this is what's known as the Fourier transform, okay? So the Fourier transform we'll write, remember when we did the Laplace transform, we wrote Fs, right? Here we're going to write F omega. And then remember how last time with Laplace, we did, the cursive L, and then, curly brace the function. Here we're going to do a cursive big F, ft, okay? And again, the Fourier transform is integral from negative infinity to positive infinity, f of t, e to the minus j omega t dt. Now, this should look pretty familiar, right? It looks pretty much the same thing as the Laplace transform, except here we're integrating from negative infinity to positive infinity instead of 0 to infinity. That's what we do in Laplace. Okay, I'll just write that out so you can remember Laplace. And then Laplace, the exponential term is e to the minus st, but here it's e to the minus j omega. Okay, cool. Okay, so that is the Fourier transform right here. So now we need to talk about the inverse Fourier transform, because when we did the inverse Fourier transform or inverse Laplace transform, we kind of like glossed over a bit. I think I mentioned, oh, it oftentimes turns into this ugly line integral. Most of the time we just kind of use a table. The Fourier transform is not as ugly. It's a lot easier to do the inverse, and so we're actually going to look at it this time. Okay, so for the inverse, you can recall, again, the Fourier series is going to be this. Now, what we're going to do is we're going to take the Cn times and multiply by big T. Then you have e to the j and omega t. Since we multiplied by t, you need to divide by t. Okay, but remember, if big T goes to infinity, and then Cn big T, that goes to f omega, like we just showed, then n omega naught is going to go to infinity. And lastly, 1 over big T is going to go to d omega over 2 pi. Okay? So we are going to replace each one of those pieces. Okay? So the summation is now an infinite summation, so it's an integral. Okay, Cn times t, that is f omega, e to the j, and omega naught goes to infinity, t, and then 1 over big T goes to d omega over 2 pi. Now we can take this 1 over 2 pi out front of the integral, and that's usually how we write it. And we're left with this expression for our inverse Fourier transform. Okay, so I think this is pretty cool, and I actually really like how the math, I think, for me, feels fairly elegant. Okay, cool. So now I just kind of blasted you some theory, so that's probably the one proof we'll do today. So let's do an example, okay? And this is a very classic example. It should look somewhat familiar, okay? So suppose we've got sort of a box. Height is Vm. It's gonna range from negative tau to positive tau. And we kind of did this last lecture, right? So to find the Fourier transform, it's just gonna be V omega. Now this is gonna be Vt to t. So we want to take the Fourier transform of this. So v omega is, we're going to be integrating. We should normally be integrating from negative infinity to positive infinity, but as you go out to infinity, it's all just going to be zeros anyway, so we can kind of ignore that. So it's going to be negative tau to over 2 to tau over 2, Vm e to the minus j omega t dt. Okay. So we've got Vm e to the j omega t all over minus j omega. We're going to be evaluating from negative tau over 2 to positive tau over 2. Okay, then we've still got Vm over minus j omega. Now we've got e to the minus j omega tau over 2 minus e to the j omega tau over 2. Okay, Now this form should look somewhat familiar, right? It looks like a sine, again. Going back to the Euler definition of sine. You can look that up. Anyway, so we've now got Vm over j omega minus 2j sine omega tau over 2. Okay. So that negatives, those are going to cancel. Those j's are going to cancel. Okay. But I mean, we're going to like this particular form, so we can write it now as Vm times tau times sine omega tau over 2 all over omega tau over 2. Okay, so that's the Fourier transform of f of t. Now what's interesting, we notice when you actually do this Fourier transform that the final form here is going to be, it's all real valued. This is also an even function as well. Now, let me grab the book real quick. We'll see how the book plots this, rather than me try to sketch it out. The book's graphics are going to look a lot nicer whenever I can cobble together freehand. Okay, so we're going to I'm flipping to chapter 17 to page 646. Okay, so we notice there's a lot of relationship between what we did last time, because again, we did this, we took the Fourier series of a repeating version of this, right? Okay, and so that's what it would look like if you were to plot the coefficients of CNs. But if we were to take this and then tighten it up a bit, so essentially push out the period, we would see the height of the envelope would decrease a little bit by half actually, but we'd have more points in between. Similarly, if we were to keep doing this until we had the Fourier transform, we plot the Fourier transform, it looks like this, okay? So we can see that there's a huge relationship between the Fourier, the complex exponential Fourier series and the continuous Fourier transform. So that's kind of cool. Okay, cool. Let me set my book over here. Okay. So the next thing I want to talk about is convergence. And the basic idea of convergence is the Fourier transform, since it's an infinite integral, we're integrating from negative infinity to positive infinity. The integral obviously must converge. And that seems like a no-brainer, right? So for that to happen, there are two ways we can do it. The first is we could have a situation like this, where it's clearly going to converge, because really we're only integrating from negative tau over 2 to tau over 2. That's fine. Or what if we have a situation where our function is going to be, I don't know, f of t equals k e to the minus at ut, okay? So in this case, we see that this function is going to go all the way to infinity. Is it going to converge fast enough, though? This is a big question. And it turns out it is. So let's do the Fourier transform. This is a very classic Fourier transform, by the way. So we've got k e to the minus at ut e to the minus j omega t dt. Okay, since we have this ut right here, that means we only really need to integrate from 0 to infinity. Okay, I'm going to pull the k all the way out front. So we have e to the minus a plus j omega t dt. Then we end up with, we've just finished this integral up, it's going to be a over a k over a plus j omega, but that only works if a is greater than 0. If a is less than 0 or equal to 0, this is not going to converge, because then you're going to have like an exponential rise. And given the news, everyone's very familiar with the concept of an exponential rise and why that can be problematic. Okay, so that's one case. How about, here's another that's interesting. Suppose it decays exponentially to both sides, okay? And this function is going to be f of t is equal to a e to the minus just epsilon absolute value t. Now epsilon is some parameter and it's going to be greater than 0, okay, to make this work, to have this decay go to 0 on both sides. So we can set up this Fourier transform. We're going to do it in two parts. First part, we're going to go from negative infinity to 0, and the second part, we're going to have to go from 0 to infinity. So I'll set that up. So negative infinity to 0, ae epsilon t e to the minus j omega t dt plus 0 to infinity ae to the minus epsilon t e to the minus j omega t dt. Now this one we already know, right? And this one, if you do the integral, follows a very similar pattern. So we end up with a over epsilon minus j omega plus a over epsilon plus j omega. Okay, so we can simplify this down. We end up with a epsilon plus j omega plus a epsilon minus j omega, and that's all over epsilon squared plus omega squared. Okay, so we've got 2a epsilon all over epsilon squared plus omega squared. Okay, cool. So what's interesting here is now we're going to let epsilon go to 0. So in time, what this is going to look like is essentially it's just going to be constant, right? Because there's no exponential decay at all. It's just a constant value at a. And what it will look like then, if you look at this, as epsilon goes to 0, this looks a lot like a delta function. And the book goes through some stuff where it kind of more rigorously shows this is a delta function. But if we can take my word for it that f omega is going to be 2 pi a delta omega. So again, so we have another Fourier transform pair. So we can say the Fourier transform of just some constant value, a, that's going to be 2 pi a delta omega. Okay, so thus far, the Fourier transforms we've seen this one. This is the decaying exponential. We've seen this one, is kind of the, I guess, double-sided decay exponential. This is the constant. And then we also did this one, where it's just the rectangle function. Okay, so we're starting to build, some handy Fourier transforms as we go along. Now, in the book, there are tables, and so when we actually learn more about this type of stuff, when we learn about operational transforms, we'll be able to just use tables at that point and kind of skip the integral, sort of like we did with the Laplace transform. But we're not quite there yet, so we need to, do these by brute force at this point still. Okay, so let's do an example. It's going to be assessment problem 7.1. So in 7.1, so essentially, we kind of have two boxes. They're shifted like this. We see we have some odd symmetry going on, if that matters to anybody. Amplitude is a and negative a, and these go to tau over 2 to negative tau over 2. Okay. So we have f omega that's equal to, so we're going to break this into two integrals just like we did earlier. So it's going to integrate from negative tau over 2 to 0. That's going to be negative a e to the minus j omega t dt plus omega tau over 2 a e to the minus j omega t dt. Okay? So we can do these integrals pretty easily. So we end up with a times e to the j omega t all over j omega. Yeah, we don't need that negative right there. Okay, we're integrating. Wait, no, I still need that negative. Okay, that negative cancels out one from the a. Had an error in my notes. I'm gonna fix that. Okay, cool. And again, we're evaluating from negative tau over 2 to 0. And then here we have a e to the minus j omega t all over minus j omega. And we're evaluating from 0 to tau over 2. Okay. So we can just do this evaluation, simplify quite a bit. We have 1 minus e to the j omega tau over 2 minus, because this minus sign right here, e to the minus j omega tau over 2 plus 1. Okay. Cool. So I'm going to take 2 out of this. Okay, and I'm also going to move that j to the top. So now we have minus j 2a over omega. And then 1 plus 1 would be 2, but we took the 2 out already, so that's just 1 now. And this, again, is an Euler identity for a cosine. So it's minus cosine omega tau over 2. Okay, cool. So let's do another example real quick. So this one is going to be f of t is equal to t e to the minus at ut. Okay, so we set up the Fourier transform. It's f omega equals negative infinity, positive infinity, t e to the minus at dt. Ut, I'm not done, e to the minus j omega t dt. Okay, so we can simplify this integral quite a bit because we have that u of t, and I'm going to combine the exponentials. So we have t e to the minus a plus j omega t dt. Okay, at this point though, you can see quite quickly that this is an integration by parts problem. And that's fine. Or you can just use the table in the back of the book. At this point, I don't care what you do. So u is going to be t, so du is going to be dt. dv is going to be e to the minus a plus j omega t dt. And then v is going to be e to the minus a plus j omega t all over minus a plus j omega t. Okay, cool. So now we can just use this instead of the integration by parts stuff. So we have minus t e to the minus a plus j omega t all over minus a plus j omega, evaluate from 0 to infinity. Then the second integral part, 0 to infinity. Then we just have e to the minus a plus j omega t all over minus a plus j omega. And this is dt. Okay, cool. Now guys, one thing that's interesting about this is this first term right here is all going to go to 0. And the reason for that is if we put t be infinity, that term's going to go to 0, though you have this infinity term right there, which is kind of weird. You can use L'Hopital to verify that I'm not lying to you about this. But yeah, so this whole thing goes to 0, and then you plug 0 into this, into t, and that 0 cancels that out. So we're only left with this second integral, which makes things easy. So I'm going to just cancel these negatives. And that's the integral we need to solve now. Okay, so we do that, and we end up with minus a plus j omega t all over a plus j omega squared, evaluated from 0 to infinity. Oh, we had to bring the negative down again. We evaluated infinity, that top term goes to 0, and so we end up with just evaluate at 0, evaluate at 0, and that goes to 1. So we end up with 1 over a plus j omega squared. Cool. Okay, that's not too bad. Okay, let's do one more example. Okay, so this is assessment problem 17.2. In this example, we have this function, it's more or less given to stepwise. Okay. And here are the points where things change at -3 and 2 and 2 and 3. Okay. The heights are going to be 1 and 4. Okay. So what we want to do in this is, this is the Fourier transform of the function. Okay, so we want to take the inverse Fourier transform. So essentially, we just go back to the fundamentals and write out the Fourier definition. Okay, so we take the first block, so it goes integrating from -3 to -2. Amplitude is, the function value is 4, e to the j omega d omega, plus 1 over 2. Here we're going to go from -2 to 2, and the amplitude here is 1, so it's just going to be e j omega d omega, plus 1 over 2 pi. And we're integrating now from 2 to 3 for e to the j omega d omega. Okay, so now we just have these three very simple integrals to worry about. Oh, sorry, and then we need omega t, omega t, omega t. Yikes. Okay, so we're going to pull that 1 over 2 pi all the way to the front. And at this point, we were just going to start evaluating things, or doing these integrals. So now we have e to the j, 4 e to the j omega t over jt, okay, because the integration variable is omega now, -3 to -2, plus e to the j omega t over jt, evaluate from -2 to 2, plus 4e to the j omega t over jt. We're going to go from 2 to 3. Okay. Now, this is just a lot of math, guys, at this point. It's not too bad, but it can be tedious. I'm going to pull out these jt's. Okay. And I'm just going to evaluate each one of these pieces. So now we've got 4e to the minus j 2t minus 4e to the minus j 3t plus e to the j 2t minus e to the minus j 2t plus 4e to the j3t minus 4e to the j2t. Okay? Cool. So now we can start grouping some terms and just kind of simplifying this a bit. That's a t. So here, that's e to the minus j2t, so we can combine, we can add these together. 4 minus 1 is 3. Okay. This one, that's not going to combine with anything. But this one's going to combine with this one, right? So now we have minus 3 e to the j2t. And then we've got plus 4 e to the j3t minus 4 e to the minus j3t. Okay, cool. So we already have this, we can actually bring this 2j in for each term, so we can get rid of that. Okay, we see that as a sign, and that's a sign as well. It's using those Euler identities. So the final answer is going to be 1 over pi t. So this is going to be just 4 sine 3t. And then this is going to be minus, because the positive exponential is the first one, and that's negative here. So minus 3 sine 2t. Okay. Cool. So these aren't too bad. Most of the time when you get a function, you need to take an inverse or forward Fourier transform. They're going to be usually pretty easy. Yeah, because you can only do so much with these integrals. Like I said, ultimately we're going to end up moving to like a table-based approach, which is going to make our lives a lot easier. Okay, but we're not quite there yet. Next lecture. Okay, so the next thing I want to talk about is how this relates to the Laplace transform. Okay, so remember in the Laplace transform, the variable we want to find is, the function usually ends up like f of s, right? So suppose that we have a function, f of t is equal to e to the minus at ut. The Laplace transform then is going to be 1 over s plus a, right? Okay, so s is the sort of the variable in the Laplace domain. Okay, now remember also that s is a complex number, and we could break it down into 2 parts. You have a real part, that's sigma, and then the other you have an imaginary part, which is j omega. Okay, now we see that j omega looks pretty familiar, right? So essentially, you can say that the Fourier transform is just a Laplace transform where you replace the s with j omega. And I'm going to show you how that works. Okay, so if you were to write it out formally, we can say that f, so the Fourier transform of some function f of t, is the Laplace transform of f of t, but we just let all the s values be j omega. Okay, but there's a big if. If f of t is equal to 0 for all t greater than 0. So essentially, less than 0. That's a big deal. So essentially, this only works if the function we're taking the Fourier transform of is 0 where t is negative. Okay. So, for example, let's look at an example. And the reason for that is because we defined the Laplace transform we dealt with the unilateral Laplace transform, so we usually go from 0 to infinity f of t e to the minus st dt. So we'd have to say the same thing for a Fourier transform where we evaluate it from 0 to infinity f of t e to the minus j omega t dt, right? So if the function, this integral is valid if this function f of t is 0 for all negative numbers, or for all negative t. So let's look at an example of why this might be handy. So suppose we have a function e to the f of t e to the minus at cosine omega naught t ut. Okay, so because of that heaviside that step function, you know, this is clearly 0 where t is negative, right? So if we take the Laplace transform of this, you guys should remember this. We've seen these a lot when we have, you know, complex roots for Laplace. So this is the Laplace transform for this. Okay. So if we want to take the Fourier transform of this, I mean, sure, you could throw this in an integral and solve. It'd be horrible. I don't even know if you could get there, to be honest. But we could do, to make our lives easier, we can say that the Fourier transform is just the Laplace version. Evaluate s equals j omega. So essentially, I just take the Laplace transform, replace every s with j omega. And that's it. Okay, so that's pretty awesome because it just made our lives so much easier. Now, granted, you could simplify this, you know, quite a bit if you wanted to. Okay, but like I said, this is only good if f of t is 0 where t is less than 0. Okay, now what happens if f of t is equal to 0 for all t greater than 0? So essentially it's the opposite, where f of t is defined where t is negative, but it's all 0 where t is positive. Okay? So, formally then, the Fourier transform in this situation is just the Laplace transform, but we replace the t's, so essentially we flip f of t around the y-axis. Okay, and then we evaluate s equals minus j omega. Okay, so we can do an example. We'll sort of do the same example. So suppose we have f of t equals e to the at cosine omega naught t u minus t. Now, if we were to plot this thing, so just to sort of show you the behavior here, we were to plot this, it's gonna sort of be decay envelope as time goes to negative infinity, but on the positive side, everything's 0. Okay. So to do this, then, we want to take the Laplace transform. If this thing after we flip it, around the y-axis, okay? So we just replace all the t's with negative t, so e to the minus at cosine omega naught minus t u t. Okay, now fortunately cosine's an even function, right? And so if it's negative t or positive t, it doesn't matter. Okay, so this is equivalent to e to the minus at cosine omega t omega naught t ut. Okay. Oh, and again, this is evaluated s equals negative j omega. S equals negative j omega. Okay, cool. And we know the Laplace transform of this. And so we end up with just minus j. So I'm replacing all the s's in the Laplace transform, minus j omega plus a all over minus j omega plus a squared plus omega naught squared. Okay. Now, oftentimes we have a function that, you know, is not strictly negative, where they're only, where the function is not, where it's defined, I guess, you know, on both sides of the axis. Okay. So, for example, we saw this one earlier. Suppose we have, we'll call this f of t is equal to the is equal to e to the minus a absolute value t. Okay. So the f of t is non-zero on both sides of the axis, but it's even. It doesn't have to be even. That's fine still. So we can break this into two parts. Okay. So we have f of t is equal to f plus a t. So that's pretty much all the stuff on the right-hand side of the y-axis, or the positive side, plus the negative side. Okay. So we can say that the Fourier transform of f of t is equal to the Fourier transform of the positive side plus the Fourier transform of the negative side. Okay, that's equal to the Laplace transform of the positive side, evaluated s equals j omega, plus the Laplace transform f minus t, or f minus negative t, s equals minus j omega. Okay, so let's do an example of this. So again, consider this function. We already did this sort of by brute force, but we can say then is f omega is equal to 1 over s plus a, s equals j omega. This is from the positive side. This is pretty straightforward. On the negative side, again, we flip the negative side, and we have pretty much the same Laplace transform, so it's 1 over s plus a, evaluated s equals minus j omega, okay? And that's equal to 1 over j omega plus a plus 1 over minus j omega plus a. And again, we can simplify this. We end up with 2a over a squared plus omega squared. Okay, cool. So there are a lot of tricks to save us from a lot of integration. I guess that's kind of the bottom line here. Okay, some functions get kind of difficult to find the Fourier transform of. So we might sometimes have to use limits. So for example, what is the Fourier transform of u of t? Well, that becomes tricky because that integral is not going to converge. But I promise you guys, there actually is a Fourier transform of the step function. So to find that, the Fourier transform of the step function, we need to define a new function. It's called the sinem function. Okay, so I'm introducing a new function. Now the sinem function is pretty straightforward. Its values are either 1 or -1, whether or not t is positive or negative. So essentially, it'll tell you whether or not your t, if your t is positive, it returns a positive 1. If your t is negative, it returns a -1. Now, you might think that's kind of a stupid function, but we can define sinem of t as u of t minus u of minus t. Okay? Now, what we can do is we can take the limit as epsilon goes to 0, and what we're going to do is we're going to define this in terms of decaying exponentials. Okay? As epsilon goes to 0, that turns into a u of t, right? And same thing with this one. Okay, so we can take the Fourier transform of a sine function okay, s plus epsilon s equals j omega, again because we knew the Laplace transforms of this, so it's 1 over s plus epsilon s equals minus j omega. Okay, so now replace our s's. So we have 1 over j omega plus epsilon minus 1 over minus j omega plus epsilon. And again, I apologize, you can hear the creaky floors from above. One of these days, I'm gonna have to replace my subfloors in my house, but that's not gonna be anytime soon. So until then, we were gonna have to bear with my family walking around upstairs. Anyway, so we can simplify this down quite a bit, and we end up with minus 2 j omega squared plus epsilon squared. Okay, now if epsilon were to go to 0, then we could say then that we would see that f omega here would then go to 2 over j omega. Okay, so when it's all said and done, the Fourier transform of a sine function is just going to be 2 over j omega. Okay, now we're going to use the sine function to define our step function. So I'm going to argue that a step function ut is equal to 1/2 plus 1/2 sine function. Okay, and the reason for that is essentially I squeeze this down by 1/2. Okay, and then I move everything up by 1/2. Okay, so here where it was negative 1/2, now it goes to 0. Where it was positive 1/2, it just goes to 1. So now we have a step function. Okay, so we can take the Fourier transform of this. And then we know the Fourier transform of 1/2. Okay, we mentioned that earlier. What happens when you take a Fourier transform of just a constant? It's just pi delta omega. And then we take 1/2 the Fourier transform of the sine function, and that's going to be plus 1 over j omega. Okay, so that's how we take the Fourier transform of a step function. So that's kind of weird. Now the Laplace transform, if you remember, the Laplace transform of a step function is very different. It's much more simple. It's 1 over s, right? Where here, you'd think would be just 1 over j omega, but you have this additional delta function term as well. And there are a lot of details as why that's the case, and I'm not going to get into right now. We'll talk about it more next semester in 3210. Okay, so the last thing I want to run through is how to take the Fourier transform of just a cosine. So cosine also is going to take a bit of a trick to do that, because if you were to take this and throw that in the integral, you wouldn't be able to solve it pretty much. It'd be hard. So we're going to have to go backwards. Okay, so remember that so suppose we have a Fourier transform that's f omega is equal to 2 pi delta omega minus omega naught. So it's a shifted delta function, not a delta function that's centered, but one that's been shifted. Okay, so we take the inverse Laplace, or the inverse Fourier transform of this. and we set up the integral. Okay. Oh, that's d omega because we're taking the inverse. Okay. So when we take the, well, we see first, these are going to cancel. Now this turns into a sifting problem, right? Because we're going to replace the ne omega and the e to the minus j omega t with omega naught, and then we can pull it out. Okay, so we have e to the j, or e to the minus j. Ooh, making all sorts of mistakes. Okay, because it's inverse, you have a negative j omega t. So you can pull out this e to the j omega naught t. And then we just have an integral over delta function. And we know what that is. That's just 1. Okay. So we now have a new Fourier transform pair. Essentially, anytime you have a complex exponential, its Fourier transform is 2 pi times delta, the shifted delta function. Okay, so remember the Euler identity for a cosine and how that's equal to e to the j omega naught t plus e to the minus j omega naught t all over 2, right? So we can take the Fourier transform of this cosine term and then we have 1/2. And we're going to take the Fourier transform e to the j omega naught t plus Fourier transform e to the j omega naught t. Okay. So the 1/2, we know that Fourier transform, we just showed it. And this one you can just say is more or less omega. Omega naught is just negative omega naught, and so this turns into 2 pi delta omega plus omega naught. Okay. So those twos are going to cancel. So what we end up with is pi times 2 shifted delta functions. Now this concept is pretty critical, and we're going to pretty much, we'll run with this pretty far in signals, not so much in this class, but I just wanted you to be exposed to it. Now, I don't know who the person who came up with this was, you know, the proof to get to this. That is well beyond my ability. But that's what the Fourier transform is of a cosine. So you need to be aware of that. Now, do you need to be able to reproduce this work to get here? Probably not for this class, but I just wanted you to be aware of it. Yeah, so that's pretty much everything I have today for the Fourier transform lecture. We're gonna spend, so that pretty much wraps up the lecturing for this week. So next week we have really 2 more weeks of instruction until we wrap up the semester. So next week we're going to do 1 more lecture on just Fourier transforms, so pretty theoretical. Then we go back into frequency response of circuits. So we're going to go back in the book a little bit and talk about frequency response after we've covered all this, and a bit into filter design as well, which I think is the most entertaining part of this class. So, yeah. So I guess I'll see you next time.